Hello guys, today we will study on the topic solid and semiconductor devices. Second, first PN junction diode, second forward bias of junction diode, third reverse bias of junction diode, fourth diode characteristic, fifth static and dynamic resistance of a diode, sixth diode as a half wave rectifier, seventh diode as a full wave rectifier. P-N junction diode. When a P-type semiconductor is joined to N-type semiconductor such that a crystal structure remains continuous at the boundary, the resulting arrangement is called a P-N junction diode or a semiconductor diode or a crystal diode. We can see the structure of P-N junction diode. Mobile hole majority carrier, immobile negative impurity ion, mobile electron majority carrier, immobile positive impurity ion. When a p-n junction form, the p region has a mobile holes positive and immobile negative charge ion. N region has mobile electrons negative and immobile positively charged ion. The whole arrangement is electrical neutral. For simplicity, the minority charge carrier are not shown in a figure. P-N junction diode immediately after it is formed. We can see on the diagram depletion layer, FR, and electron. After the p-n junction diode is formed, first holes for p region diffuse into n negative due to difference in concentrations. Second, free electrons from n negative regions diffuse into a p region due to the same reason. Third, holes and free electrons combines near the junctions. Fourth, each recombination eliminates an electron and a hole. Fifth, the uncompensated negative immobile ion in the p region do not allow any more free electron to diffuse from n region. The uncompensated positive immobile ion in the n region do not allow any more holes to diffuse from p region. Seventh, the positive donor ions in the n region and the negative acceptors ions in the p region are left uncompensated. Eighth, the region containing the uncompensated acceptors and donor ions is called depletion layer region and depletion layer because this region is devoid of mobile charges. Since the region is having only immobile charges, therefore this region is called space charge region. Ninth, the region n region is having higher potential than p region. 10th, so an electric field is set up as shown in a figure. 11th, the difference in a potential difference So potential between P and N regions across the junctions make it difficult for the holes and electrons to move across the junction. This act as a barrier and hence called potential barrier or height of the barrier. 12th, the physical distance between one side and the other sides of a barrier is called width of the barrier. 13th, potential barrier for SI is nearly 0.7 watt and for GE is 0.3 watt. 14. The potential barriers opposes the motion of the minority carrier. 15. However, a few majority carriers with high kinetic energy manage to overcome the barrier and cross the junction. Potential barrier have to movement in a minority carrier. Forwardbias. We can see on the diagram when the positive terminal of the battery is connected to the P region and the negative terminal is connected to N region, then the PN junction diode is set to a forward bias. First, holes in P region are repelled by positive terminal of the battery and the free electron repelled by negative terminal of a battery. So, some holes and free electrons enter into a depletion region. Third, the potential barrier and the width of a depletion region decreases. Therefore, a large number of majority carriers diffuse across the junction. Holes, current, and electric current are in the same direction and add up. Once they cross the junction, the holes in N region and the electron in the P region become minority carrier of a charge and constitute minority current. For each electron hole recombination, an electron for the negative terminal of the battery enters the N region and then drifts towards the junction. In the P region, near the positive terminal of a battery, an electron break covalent bond in the crystal and thus a hole is created. The holes drifts towards the junction and the electron enters the positive terminals of the battery. 7th, thus the current in the external circuit is due to movement of electron. Current in P region is due to the movement of holes and current in N region is due to movement of electrons. 8. If the applied potential is increases, the potential barrier further decreases. As a result, a large number of majority carrier diffuse through the junction and a large current follow. Reversebias. We can see the diagram. Depletion region. When the negative terminal of the battery is connected to P region and positive terminal is connected to the N region, then the PN junction diode is said to be reverse bias. First, hole in the P region are attracted by negative terminal of a battery and the free electron are attracted by positive terminal of the battery. Thus, the majority carriers are pulled away from the junction. the potential barrier and the width of a depletion region increases. Therefore, it becomes more difficult for majority carriers to diffuse across the junction. But the potential barrier helps the movements of the minority carriers. As soon as minority carriers and are generated, they are swept away the potential barrier. At a given temperature, the rate of generation of a minority carrier is constant, so the resulting current is constant irrespective of the applied voltage. For this reason, this current is called reverse saturation current. Since the number of minority carriers is small, therefore this current is small and is in the order of 10 nano ampere in a silicon device and 10 की power minus 6 ampere in a germanium device. The reverse bias PN junction diode has an effective capacitance called transactions or depletion capacitance. PNN regions act as a plate of a capacitor and the depletion region act as a electric medium. Diode characteristics. Forward bias. We can draw a circuit of forward bias and the forward bias graph. VK is a new voltage. Reverse bias resistance of diode. First, static of DC resistance R dot DC is equals to V upon I. Dynamic or AC resistance R AC is equals to delta V by delta I.